Okay, now we're going to return to chapter 2 to finish up the last half. A little bit about climate and a little bit of a deeper dive about the PDO. So we got to get through a few more kind of just general kind of review climate terms to make sure we're all on the same page, and then move into a little bit about the PDO. Sorry. So additionally, vegetation can influence climate. Albedo, which is just the amount of solar radiation that the surface reflects. And lightly colored surfaces reflect more energy. And so that's one thing that we talk about as we're losing snowpack, glaciations, permafrost, things like this. That's not only the loss of that physical ice, but now that ice is gone, albedo is changing. So ice has high albedo, it's white, that goes away, and we're left with darker soil that absorbs more energy. And so it's kind of a ratchet, one term I use, which means it's easier to go one way and harder to go the other. Like a ratchet does work in one way and then slides back. It's a bit of a ratchet or slippery slope or spiral effect, any kind of analogy like that you want to use to realize that it's easier to decline than it is to improve. And as true for many ecosystems, that they're easier to destroy than they are to fix. Albedo gives us one way of thinking about that in relationship to loss of ice, as well as we'll look at a couple other factors that I think are pretty interesting. The next is that a coniferous forest has a dark color and lower albedo than bare soil or dormant grassland, and it absorbs more energy. This is one I hadn't really spent that much time thinking about because I'm not a terrestrial person, but when you read it, it makes sense. And you can think about looking at the Northwest on Google Earth or through any other satellite imagery, and you see the dark patches, and you see maybe lighter grasslands or fields. And in the state of Washington, we actually have a lot of grassland. And so that absorbs less energy than a darker coniferous forest would. This is also kind of interesting to think about, that the texture of the Earth's surface changes with vegetation. And again, like I'm a marine person, so I've got a lot of analogs in the marine environment, but the example used here is a continuous grassland has a smooth surface, which allows greater transfer of energy to atmosphere by wind than a rough surface, such as a mixed forest and grassland. So what that's saying is that if you have a big grassland and wind blowing across it, that wind will efficiently pull heat out of the land and move it into the air. Where if you have a mixed system where you've got clumps of trees and grassland, that wind is then moving along the grassland and then going up over the trees and back down, and it's breaking up a bit more, and those trees are like acting like islands that help keep that area insulated. And so and you can think about that too if you're ever been out at night. It's warmer when underneath trees than it is out in the open, and that's one reason, is that it sort of forms an insulative barrier where wind can't effectively move through there, and as it moves through there, it's taking heat and moving that around the climate system. So it's pretty interesting to think about how habitat heterogeneity and the type of plants impact transfer of heat, which is, perhaps not something we normally think about. And vegetation can also cool the atmosphere through transpiration, which is evaporation from water from the plants and leaves. So plants transpire water. I mean, they use a lot of water, and that's where a lot of it goes, is it evaporates into the atmosphere. So this evapotranspiration is loss of water plus evaporation from the soil. And so that's one way that air is cooled. And we talk about that transfer of heat as latent heat, the transfer of energy. And so what deforestation can increase the albedo of land, so that's increasing the amount of energy that's reflected back up, decreasing the amount of energy that's absorbed, because now we've gone from a dark conifer forest to something lighter. There's less absorption of solar radiation, okay, and less heating, so that's the change in albedo. But that's offset by less cooling by evapotranspiration. So if you go from a forest system, it's absorbing more energy, but it's also cooling via water. The evaporation is a mechanism for cooling. You remove that forest, now you've got less energy absorbed, because now you've got a lighter colored vegetation, but you also have less water going up in the atmosphere via evapotranspiration. So this results in less moisture in the atmosphere and then less precipitation. So deforestation in the tropics can lead to warmer, drier regional climate. So you actually impact the overall climate system by forest practices or land practices that reduce the amount of water that make it up in the atmosphere. So these can have really large impacts. These localized management decisions can have large local or large regional impacts. So this image kind of shows two systems: a vegetated system, so a lot of evapotranspiration, latent heat loss moving up into the atmosphere, creating precipitation, some degree of albedo, some relatively less albedo, so there's more absorption of the sun's energy, but not. And in this deforested system, you've got more reflection of the sun's energy, but less evapotranspiration. Sensible heat loss comes from the wind example, right? So in a flat system, you'll have more heat transferred into the atmosphere because that wind is moving across the flat plane. Where in the vegetated system, you have less sensible heat loss because the wind is moving up over the canopy, not through the forest, and so there's sort of an insulation factor that's happening there. So while it might be counterintuitive in that the deforested area is reflecting more energy via albedo, it's actually making the system warmer overall. And those two mechanisms are increased sensible heat loss and decreased evapotranspiration. So while it's, again, counterintuitive, those two factors, sensible heat loss and latent heat loss via evapotranspiration, change that equation pretty heavily. And we'll talk a bit about aquatic systems, primarily stratification, which is true in aquatic, freshwater, and marine systems as well, and very important, and we'll reference it again with PDO. So aquatic systems experience seasonal temperature variation that really defines those systems as well. That temperature layering is really important. Anyway, I'll get into it in the next slide. And it was interesting that ice has a higher albedo than open water, which prevents warming of the water. So once it's iced over, there's again sort of a ratchet to keep it wanting to be iced over. Whereas if the pond has an open hole in the middle, then that water, that energy from the sun can hit that water and warm it and sort of increase the melting. So if you can imagine two ponds side by side, one is totally frozen over, the other one has a hole in the middle, experiencing the same weather. The one with the hole in the middle the ice will melt much faster because the sun's energy is absorbed more readily by the water compared to the ice, and so it's a mechanism for heating, where the one that's totally iced over will resist any melting a lot longer. So oceans and lakes can become stratified. This is purely based on density. Typically, it's related to temperature in freshwater systems for sure. In marine systems, it's due to both temperature and salinity. And the interesting thing about water stratification is you can have two layers of water right on top of each other. And they don't mix, they don't interact. And so it's not quite like an oil and water example, but effectively it is. Meaning if you have oil or water and oil on top of it, they're not exchanging oxygen, they're not exchanging nutrients, they're totally separate fluid bodies, parcels of fluid on top of one another. It's effectively the same when you've got cold and warm water. They form layers, and oxygen is not exchanged, nutrients aren't exchanged, they're totally separate from one another. And that can cause a lot of issues where if the surface water has a lot of phytoplankton growing in it, it'll have a lot of oxygen, and that phytoplankton and zooplankton and other things are dying or defecating, and that material is flowing down to your lower body of water, which isn't able to get new oxygen from the atmosphere because it's trapped off by this upper body. And that dead material and fecal matter will decay, be consumed by bacteria, which will consume oxygen and ultimately lower the oxygen level in your lower levels. So even though you can have really, really high oxygen and just a few feet deeper, it'll be a totally different system. It's really interesting and kind of the foundation of most fresh and marine work looking at lakes, oceans, etc. So here's kind of the classic examples of a lake. This graph is pretty similar to what we use in oceanography. We've got our temperature along the x-axis, and on the y is depth. And this is set up to be thinking if you're at the surface here, and say you lower an instrument down, what temperatures will it be recording? So in the winter, it's often, we have this kind of inverse relationship where it's very cold at the surface. You lower a thermometer down, and it's pretty much 5 degrees all the way down. During the spring and the fall, when you have turnover, it's more or less the same temperature from top to bottom, a slight decrease in temperatures to go down. But in the summer, we get a stratified system where the epilimnon is warm and about the same temperature. So here's 25 degrees straight up and down. So this is a separate body of water, effectively, a separate layer of water. Then you have the thermocline, which thermo, temperature, cline, gradation. And that thermocline here, it's pretty broad. In actuality, they're pretty short. And then this deep water down here in the hypoliminon. And this water and this water are not interacting. So you've got phytoplankton growth, fish defecating, copepods defecating and dying, and all of that organic matter is exported down, falls down, and then bacteria consume that, and as well as oxygen when they break down that organic matter, release carbon dioxide and create a hypoxic area, an area with low oxygen. Then in this fall, when the weather cools, this temperature graph, this summer temperature moves more over here, and you've got the same temperature from top to bottom, as well as high winds in the spring and the fall, which then turn the pond or lake or whatever over. So it's a very important yearly cycle. And then when that happens as well, that brings all of the nutrients that have been trapped down here back up to the surface. And so it both replenishes the oxygen at depth and it replenishes the nutrients in the surface water. Now back to climate variability. On short climate scales, in the Northwest, hopefully we're familiar with these terms, generally called ENSOs, El Nino Southern Oscillation Events, which is a change in the high and low pressure cells over the equatorial Pacific that leads to changing of the trade winds. This has big impacts for the climate or weather patterns. It's a climatic anomaly manifest in weather. So whether it's an El Nino or a La Nina season, makes a big impact for what our experience is going to be for that year. La Nina is like thought of as like a reverse phase El Nino, but it can have kind of usually the opposite sort of impacts as far as what weather we can expect. Generally in South America, this results in smaller fish harvests, and they typically come after a strong El Nino, although the El Nino La Nina thing, again, with a lot of these patterns, they don't always follow one-to-one. There's a lot of variability that goes in there. They're kind of weird to think about. It's almost like this episodic global tide that pushes La Ninas and El Ninos. So these INSO events are associated with unusual climate patterns, even in distant places. And we can go back in geological records and reconstruct these INSO events that have been happening for tens of thousands of years. Generally around here, when we think of El Nino conditions, we're typically warmer, and we can be warmer and drier as well, but typically an El Nino year would be a warmer year for us. La Nina years can have a lot of rain as well. And supposedly we're in a mild La Nina, so Mount Baker is expecting a lot of snow this year. Now I want to dive a little deeper into PDOs, Pacific Decadal Oscillation. I'll talk a bit about salinity, which is the concentration of dissolved salts. Salinity and temperature are the two drivers of density, the two main drivers of density in the ocean. It depends on where you are, which one's more common or more powerful, but salinity is frequently a big one because density of water changes a lot as you add salt to it. And the open ocean salinity varies from 33 to 37. In Puget Sound, 28 is our average salinity, so we do have a fair amount of freshwater input in Puget Sound. And I'm careful to say Puget Sound, not Salish Sea, because it's different. Not necessarily between Vancouver Island and mainland, but in the Straits, it's saltier. But Bellingham Bay, surface water can actually be very fresh, depending on where you're at in relationship to the Nooksack River. But out by Eliza Island, on the other side of Lummi Island, 28, pretty common for Puget Sound. So, and we are a fjord system, and that is represented in that lower salinity compared to oceanographic, to pure ocean water. And there's a couple terms around low oxygen. Generally, I try not to use anoxic, because anoxic means no oxygen. I typically use hypoxic, which means low oxygen. There are examples of anoxic conditions, zero oxygen, but generally we're talking about hypoxic conditions, low oxygen. Particularly when we're talking about, hypoxic conditions led to a fish kill. They probably killed fish, but there's maybe a small amount of oxygen and clams are able to survive, things like that. Every organism has a different oxygen level that it needs to maintain life. And so you can have hypoxic conditions and kill a suite of organisms and not another. Under anoxic conditions, then every organism that uses oxygen for respiration would die. Organisms that use chemosynthetic pathways, like those that form hydrogen sulfide, H2S, are fine. But those are anaerobic bacteria. So try to use the word hypoxic. It is much more correct. In the ocean, a lot of this has to do with that gradation we talked about, with primary productivity happening in the surface layers, export of organic material that decays and decomposes, consumes oxygen. The inverse of that, I guess, would be as you move up mountains, there's less oxygen, and part of that is thinner atmosphere. So let's talk a bit about PDO. Research on salmon production led to the discovery that PDO is this 20 to 30 year oscillating cycle of warm and cool temperatures in the North Pacific, and these phases influence marine ecosystems. Salmon, they have big impacts to invertebrates and groundfish as well. Groundfish, hake is a big one, cod, halibut, rockfish, etc. And so through its climatic effect, the PDO also influences the functioning of terrestrial ecosystems. So what happens in the ocean happens on the land, movement of precipitation, temperature, etc. And the PDO, the root cause is still unknown. Like these are, again, like these weird pulsations that happen in our climate that we're not fully able to understand the drivers behind them. But based on long-term data sets, like reconstructing salmon populations from isotopes in lakes, things like that, tree rings, you can build back PDO records that go back a few hundred years. And so it's been happening for a long time. So we're going to look at this first paper here, or we'll talk about this first paper here. I'm trying to think if I have a graph for it. No, this paper just came out in March of 2020, and it's thinking about what does the PDO mean in the most recent decades. And so a lot of the PDO work happened in mid to late 90s throughout the 2000s, and it was really focused on this 77, 76 shift. And it hasn't, like the role of PDO in salmon predictions has kind of fallen apart the last few years. And so what I'm going to describe is the PDO. There's still something there, but some of those mechanisms might be falling apart. And it could be something like fishery populations are now very altered due to fishing or other influences that climatic effects are hard to measure given all the other noise. But there's sort of kind of growing questions about what does the PDO look like going in the future. And granted, it is very hard to predict the future. So this graph has a PDO index in it with salmon. Positive PDO means warmer water pool, and then blue means negative, cooler pool associated with the PDO. And in the next graph, I'll describe what that means. But basically, the nearshore areas of warmer with positive PDO off Alaska, and it's cooler with a negative PDO. So this is positive PDO, warm year, cold. This is showing salmon returns, departure from the average, so showing lower than average salmon returns. It's that 77 shift up until 98, I think, is the other shift here. And this is arguing that when PDO is positive, there's less salmon returns. Now that's for the Columbia River, and they don't fully articulate that in the book, but that's for the Columbia River, and it's actually a pretty interesting system where it causes a flip-flop between winners and losers, either Washington or Alaska. So we're going to walk through that a little bit more, but this positive PDO is associated with negative salmon returns, is associated with the Columbia River. Here's an example of what the PDO could look like. So this is difference from average. So we have a cooler tongue of water coming in here and a warmer surface water near shore. Now that's interesting to me because typically, like we mentioned, upwelling brings cold water, and so typically having warmer nearshore waters is actually a bad thing. In Alaska, that stability is actually what's required, meaning that in many areas in Alaska, it's not an issue of needing more upwelled nutrients. It's an issue of needing warm, stable water to allow the phytoplankton to grow and use those nutrients. Whereas in more southern areas, it's a lack of nutrients that's the issue. And so warmer, more stable waters with less upwelling causes a negative to phytoplankton growth. So that same climate impact impacts different areas differently. How many times can we say the word different? So northern areas, they really need stability. There's already a lot of nutrients. There's a lot of mixing. What's lacking is stability. Warm water brings stability, nice fat warm layer. There's already a bunch of nutrients. Now the water's stable. Those phytoplankton can grow and be happy. In southern areas, that warm water could depress upwelling and impact it there. Additionally, you have a big temperature gradient here. That's usually good in the open ocean. A big temperature gradient causes gyres and mixing, and that's typically where you see the most amount of productivity, is where two thermoclines really collide. And so if you're a tuna fisherman in Washington or Oregon, you're watching real-time satellite sea surface temperature all the time. And you're looking for a big pool of warm water coming up against our cold water, because that's where the tuna congregate, because that's where the bait fish congregate, because that's where the phytoplankton, that's where the zooplankton are, because that's where the phytoplankton are. So generally the open ocean is a vast desert. There's very little productivity. It's clear water. There's not a lot of fish. They congregate at these really steep gradient temperatures because there's a steep gradient between nutrients in mixed up water that's not stable and water that's stable but has no nutrients. And when those two collide, you have a combination of temperature and nutrients, or stability and nutrients, which can quickly lead to phytoplankton, which quickly leads to zooplankton, fish eating zooplankton, bigger fish eating smaller fish, etc., etc. So that's also really, really interesting. This is from Hair 99, and I realize that these are like antiquated graphics, but I think it's interesting. So this is that same graph here, but presented like an oceanographer would present it. So just like you're looking at a, I was going to say bathymetry, but a topographic map, you're looking at topography, and you see all the lines really, really close to each other, you know that's a really steep area. So if you're trying to decide which way to hike over a mountain and you see a bunch of lines right next to each other, that means you're looking at a cliff or a very steep area versus lines that are more spaced out. In a topographic map, each line might mean 100 feet, 1,000 feet, etc. Here, these lines are representative of temperature. These are SST anomalies, meaning sea surface temperature above normal or relative to normal. So here we have negatives, so it's cooler here than the baseline conditions, and here it's warmer than the baseline conditions. And here you can see those lines stacking up right on top of each other, meaning that over a short area there's a big gradation in temperature, which is again what we want for a lot of productivity. And then here is a stress vector, which can show like those differences in temperature and how it would relate to winds. So this is interesting. I'm going to walk through this. This is from that same Hair 99 paper, and they were looking at a bunch of different climate factors and a bunch of different biological factors in these models to see what was correlated. And there's catch data and catch data with climate. So catch data is basically PDO and some catch data, and this is catch data and adding in additional climate factors, INSO condition, and a couple other climate indices. It doesn't really matter which one we go down, but let's walk down the catch and climate one. So when PDO is positive for Western Alaska, we've got our 5 major salmon species: sockeye, pink, chum, coho, and chinook. 5 major commercial salmon species. When PDO is positive, catch here is also positive, primarily for sockeyes, really strong and weakly strong with the other ones. Central Alaska, same thing, to a much larger degree, that when PDO is positive, catch is positive. Southeast Alaska, more or less the same, kind of at the negative but near zero for Chinook. When PDO is positive, catch is positive. British Columbia, much weaker signal, some positive around sockeye, not a whole lot with pink and chum, and then now into negatives, a pretty big negative for Chinook. Moving further south, Washington, some positive with chum, negatives across the board, a big negative with Chinook. Moving further south to Oregon, where our main commercial species are chum, coho, and Chinook, and in California it's coho and Chinook. Pretty much kind of a zero, pretty much all negative. So when we have a positive PDO, it's good for Alaska fisheries, but bad for Washington fisheries. When we have a negative PDO, it's the opposite. It'll be good for Washington fisheries and bad for Alaska fisheries. So I think it's interesting that there's this like swapping of productivity up and down the coast related to this kind of large scale climate variability. This diagram kind of walks through it, like what the 60s to late 80s look like with PDO impacting the Aleutian low, wind stress, upwelling, all of these things leading to more salmon into the 90s through 2000s, potentially less. Weaker gyre, so the weaker Aleutian low, so the weaker gyre. Here we've got more rain, the kind of bigger, a bigger gradation of temperature and salinity over a shorter area, causing more productivity. So the impact of PDO really depends on where you are. Maybe it's going to fall apart in the future, but looking back over 50 years of data, there seems to be some relationship between large-scale climate variability and salmon returns, both for Washington and Alaska. So this will round up chapter 2. I'm just touching on a few main points in these lectures. There's obviously a lot more in the chapter.